Hey everyone, and welcome to today's Explainer. Today, we're jumping into a super fascinating concept from the 8th grade math curriculum. We're talking about math in motion. Specifically, we're diving into the geometry of growth, dilations, and spiritual proportions. Get ready because we're going to see how numbers don't just sit there quietly on a piece of paper. No, they stretch, they shrink, and they completely transform right before our eyes. Before we even start plotting coordinates, I want us to look at this really powerful verse. It says, "So we fix our eyes not on what is seen, but on what is unseen. For what is seen is temporary, but what is unseen is eternal." And what's actually wild here is how perfectly this mirrors our geometry focus for today. Think about it. The shapes we end up seeing on a graph, they're just the visible, temporary results of these unseen mathematical rules operating in the background. It's exactly like our own personal and spiritual growth. There are deeper, invisible principles at work shaping exactly who we become. Okay, here's our quick roadmap for this explainer so you know exactly where we're headed. We'll kick things off with the geometry of growth, then we'll move into mastering scale factors, see dilations in action, tackle the negative scale factor, practice your skills, and wrap it all up with education and morality. All right, let's jump straight into section 1, the geometry of growth. This is where we look at the exact math that architects use to scale up giant skyscrapers, or even how your smartphone zooms in on a photo. Moving right along to section 2, mastering scale factors. Let's really nail down the core math behind how things actually grow and shrink. So the absolute most important takeaway here is this definition, dilation. Basically, a dilation is a transformation that resizes a figure without changing its overall shape. It keeps all the angles exactly the same, and the sides are proportionally scaled out from a center point. Honestly, just think of it like a person growing up. Your core identity, it stays the exact same. You just got taller. Your fundamental angles didn't change, and you didn't magically turn into a completely different shape. You're mathematically similar, just a different size. And that brilliant idea brings us right to our next key term, the scale factor. If the dilation itself is the growth spurt, well, the scale factor is the DNA telling the shape exactly how much to grow. It's literally the specific multiplier used on every single coordinate of a figure to dictate how much it will expand or contract. It is the secret mathematical engine driving the whole transformation behind the scenes. Now, you might be wondering, what happens when we tweak that engine's power? Well, when we look at enlargement versus reduction, the rule is surprisingly simple. If your scale factor is a number greater than 1, say 2 or 5 or even 100, your shape is going to enlarge. It gets bigger. But if your scale factor is a decimal or a fraction sitting somewhere right between 0 and 1, like 0.5 or a third, your shape reduces. It shrinks. It is a super simple rule, but honestly, it works like absolute magic on the coordinate plane. All right, section 3, dilations in action. Let's actually apply these rules and see them work. Okay, let's get our hands dirty with example 1, enlarging triangle A. We've got our original vertices plotted, and our mission here is to perfectly double the triangle's size using a scale factor of 2. All we do is multiply the x and the y of every single coordinate by 2. So for that first point, we start at the coordinate 2, 1. Multiply both those numbers by 2, and boom, our new vertex lands right at 4, 2. The next point sits up at 4, 3. Multiply by 2, and we jump to 8, 6. And finally, 3, 2 becomes 6, 4. We just flawlessly doubled the entire size of the triangle without distorting its shape even a little bit. Now let's flip this script and look at example 2, shrinking square B. This time around, our scale factor is 0.5. Because it's a decimal right between 0 and 1, we instantly know we're looking at a reduction. So, step 1, we identify our starting vertex at 6, 4. Step 2, we apply that 0.5 scale factor. And step 3, we just do the math. What's half of 6? 3. What's half of 4? 2. We multiply both numbers by our decimal, and we safely shrink square B right down to its brand new, smaller coordinate at 3, 2. It is just a remarkably clean process. Which brings us to section 4, the negative scale factor. Get ready, because here comes a major mathematical curveball. Brace yourselves for this. When we introduce a negative scale factor, the figure resizes and it rotates. Yeah, it doesn't just change size. It literally flips entirely across the origin of the graph. It's almost like the shape is doing a cartwheel to the total opposite side of your paper. Honestly, it is easily one of the coolest visual transformations you'll ever see in geometry. Let's break down exactly how this sorcery works. Let's say we have point C sitting pretty at +2, +3. Now, we're going to apply a scale factor of -1. Watch what happens here. We multiply the 2 by -1, and we get -2. We multiply the 3 by -1, and we get -3. The new point is completely flipped to -2, -3. The shape stays the exact same size in this case because the number itself is just 1, but that negative sign, it throws the whole thing directly across the origin. All right, moving into section 5, practice your skills. It is time for you to take the wheel. So here are 5 quick missions for you to prove you've mastered these concepts. First up, try dilating point A at 5, 2 using a scale factor of 3. Second, take a triangle with points 1, 1, 2, 2, and 3, 1, and dilate it by 0.5. Third, take point B at -4, +3, and hit it with a scale factor of -2. Remember that awesome cartwheel curveball we just talked about? Fourth, figure out if a scale factor of 1.5 is an enlargement or a reduction and explain why. And finally, if a square has a side length of 8 and is dilated by 0.25, what exactly is the new length? You've got all the tools, you know the rules, and you have all the unseen math power you need to absolutely crush these. Finally, section 6, education and morality. Let's tie it all together. You know, there is this incredibly grounding quote from Romans 8, 6-7 that says, "The mind governed by the flesh is death, but the mind governed by the spirit is life and peace." I think this beautifully captures the whole philosophy of intertwining our morality with our education. Let's be real for a second. Education without morality is really just a tool, and sometimes it's a tool that can be used to hurt. But there is this deep, profound promise of peace that comes from maintaining a spiritual mind. When you combine true learning with a foundation of good character, that kind of peace actually becomes your reality. So I want to leave you with this to chew on. What is the point of being smart and supposedly highly educated if you're just going to keep making choices that hurt yourself and the people around you? Just as we use these math skill factors to carefully grow our geometric shapes without distorting their true identity, we have to use our moral compass to guide our intellectual growth. Your new math skills and your character development, they totally go hand in hand. So keep your ankles true, scale up your knowledge, and always seek peace. Thank you so much for joining me on this explainer, and I will catch you in the next one.